Okay, welcome to Klein's Geometry. We're going to look at finding the sine, cosine, and tangent of an acute angle, and then using these ratios, sine, cosine, and tangent ratio, to find side lengths of right triangles, which we can then apply to any real-world situation that has a triangular bent to it. So, looking at this, we're going to talk about in a triangle, in any right triangle, they all have a right angle, and if you were to come up here, you'd have similar triangles. If I were to look at this triangle, this triangle, this triangle, they'd all be similar. So, since they're similar, their sides would be proportional, and we can write ratios that express that proportion depending on the angle measure. So, those angles, those ratios, are the sine, which is the leg opposite the angle over the hypotenuse. The cosine, which talks about the leg adjacent to the angle and compares that to the hypotenuse. And the tangent, which compares the leg opposite the angle to the leg adjacent to the angle. When you write out sine, cosine, and tangent ratios, you get the word SOHCAHTOA. Funny little acronym, but it's a good way to remember these ratios. SOHCAHTOA. This is in your book, and we're going to talk about the big ideas on it that sometimes confuse people. Now, let's look at our right triangle. I want to write some ratios. And I have, let's say I've got angle A, angle B, and angle C. This could be any right triangle, that's why there's no measures. One of the things mathematicians will do is across from A, they'll put a little a, and that stands for this side length. Across from B, we'll put a little b, that stands for this side length, the hypotenuse. And across from C, we'll put a little c, and that would stand for that side length. So anytime you see a big A, little a, it's just the angle and the side across from it. Now, let's say I want to write ratios, trigonometric ratios for this triangle. I know those ratios are the sine of the angle, the cosine of the angle, and the tangent of the angle. Notice I didn't write out the whole word. This is what you would see on your calculator. If we want to write it out so we know what's going on, sine is spelled like that, cosine, and tangent. But this is what you see on your calculator. Now, I've got two acute angles in a right triangle. So I can get ratios for this angle and ratios for this angle. So when we think about the ratios, we have to say the sine of angle A, the cosine of A, the tangent of A. Okay, and let's just look at angle A now. So whenever I do this, I right away think SOHCAHTOA. Notice I spelled it a little differently. And I know this means the sine of the angle is the opposite leg over the hypotenuse. Now I'm looking at angle A here. Here's how I find the opposite leg. First I look at where's my hypotenuse. And you guys remember, the hypotenuse is always across from the right angle. So that is always the hypotenuse, okay, across from the right angle. Now, if I'm looking at angle A, I cover up A, and the only side I see all of is BC. So I know that's the side opposite A. So the sine of A is BC over the hypotenuse AC. Another check, if I'm looking that way, is A can't be in here if it's the opposite. And since I put letters, I could say little a, that's opposite the angle, over the hypotenuse B. So either way. And if you had numbers, you just put the numbers down. Now if I want the cosine of A, well, if I cover up A, that leg is the sine. So this is the opposite leg. So this is opposite A, which makes this leg adjacent to A. Okay? So AB is adjacent to A, and you notice it shares that point A. And the hypotenuse, again, is AC. And if you think adjacent with the little letters I used, you might put C over B, or the numbers that were there. The tangent of A is the opposite leg over the adjacent leg. So I've labeled them opposite and adjacent. So I have B to C over A to B. And that would be A over C, or whatever numbers were there. Now that's just for angle A. We also can find ratios for angle B. So if I were to do B, now I have to find a place to put it. Let's do the sine of B, and I'm just going to use the calculator term. So sine of B, that's what you'll see in your calculator quite a bit. Cosine of B, and the tangent of B. Well, this idea of opposite and adjacent to A, we don't care about anymore because we're looking at, excuse me, we can't ever use B, right, because I labeled that as my right angle. So right angles don't have ratios, okay? That's just part of the triangle. The only ratios we can find are for the acute angles. So the sine of C, the cosine of C, and the tangent of C. And this whole idea of opposite A, we no longer care about because we're looking at C. Adjacent to A, we no longer care about. We're looking at C. So now I'm going to do the same trick I did before. I'm going to cover up C. And I see this is the leg that I see. So A to B is opposite angle C. And that leaves this leg right here to be adjacent to angle C. So we got to be careful there. So now if I want the sine of C, it's the opposite. So it would be C over A, or AB over, or not over A. Sine is the opposite over the hypotenuse, so it's over B. Be very careful. Opposite over hypotenuse. Cosine of C is the adjacent leg over the hypotenuse, so this is what I labeled my adjacent leg, and my hypotenuse is B. And then the tangent of C is the opposite leg over the adjacent leg, so I go C over A. And that's how you write these ratios. They're just fractions. And in your book, you might be asked to round it to the nearest hundredths place. Remember, a fraction bar is a division sign, so it'll be this number divided by this number, rounded to the second digit to the right of the decimal. Now, let's find some of these ratios. It says, write the trigonometric ratio as a fraction and a decimal rounded to the nearest hundredth. We want the sine of J. So the first thing I do is I would think, so, ka, toa, and I think the sine, I need the opposite leg over the hypotenuse, and I'm looking at angle J. So here's J, I cover it up, and this leg, well, whoa, okay, before we do that, let's say, what's our hypotenuse? Hypotenuse is across from the right angle, so this is my hypotenuse. That makes these, the two sides of the triangle that make the right angle, those are the legs. So now I cover up J, and I see K to L, so that's my opposite leg, which makes this the adjacent leg. So I want the opposite over the hypotenuse. That's going to be 60 over 61. So the sine of J, the opposite leg over the hypotenuse. So I've got 60 over 61. Now if I want to round it to the nearest hundredth, I just turn on my calculator and I do 60 divided by 61. That's kind of hard to see. Press enter, and notice, folks, this is a 3. Go hundredth place, so tenths place, hundredths place, thousandths. It's not 5 or larger, so I just round it to 0.98. And that's all there is to it. So it's just writing ratio, like we did in chapter 7, of the opposite leg to the hypotenuse, and then rounding it to the nearest hundredth. Okay, now when we're looking at special right triangles, we're looking at those ratios, those triangles on the ceiling. So if I think about the cosine of 30, I think my right triangle, and if it's a special right triangle, I have the short leg, and I know 2 times that short leg is the hypotenuse, and I know the long leg is the short leg times the square root of 3. Recall, 30 degrees is across from the shorter leg, 60 degrees is across from the larger leg. And so if you think hypotenuse here, and we want to write the cosine of 30 degrees as a fraction. So I think sine TOA, and I'm looking for the cosine now, so I need the adjacent leg over the hypotenuse. Well, here's my hypotenuse. I cover up 30, and the leg I see is right here. I know that's the opposite leg. So then I look here, this must be my adjacent leg. So to write the cosine of 30, I'm going to say the cosine of 30 degrees equals the adjacent, some number times the square root of 3 over the hypotenuse, 2 times some number. Well, any number over itself is 1, so I can cancel those out and get square root of 3 over 2. If I was going to do the sine, once I've done all this work, it's easy enough. The sine of 30 is going to be the opposite, so x over the hypotenuse, 2x. Those will cancel out, and I have 1/2. If I want the tangent of 30, it's the opposite, x, over the adjacent, x square root of 3. Those will cancel out, and I have 1 over square root of 3. Remember, we don't leave those radicals in the denominator, so multiply by square root of 3 over square root of 3, and we'll get square root of 3 over square root of 9, 3 times 3, which is square root of 3 over 3. So there's our tangent of 30 degrees. So sometimes you'll have to do a little extra work to rationalize the denominator, but no biggie. Just a real quick, if I asked about cosine of 45, remember that that special triangle has congruent legs, x and x, and this hypotenuse is x times the square root of 2. So these are our 45-degree angles. So you could use the same process with these side ratios to find sine, cosine, and tangent of 45. Now, to find the ratio, what we've done so far is we've looked at the angle measures and we found the numerical ratio. Now, if I wanted to find the numerical ratio, it is stored in your calculator. The first thing you need to do, however, is to check your mode. So you're going to go to just to the right of the second key is the mode. And you come down here and you get either radian or degree. Notice I'm in radian and we want to work in degrees. So I'm going to arrow key down and over and press enter and say, okay, calculator, let's work in degree mode. Then I'll go second mode and I'll quit that screen. Now to find the sine of 52, I'm just going to press the sine key. It's in the middle, or the second row from the left, 4 down, and I'll pipe in 52 degrees because I just changed it to degree mode, and there's my ratio. There's my numerical ratio, the fraction changed into a decimal. So notice it's an irrational number, so whenever we work with these, don't change this to this number, just leave it as an exact answer, sine of 52 degrees when you're calculating with it, and just give us this at the very end, okay? So in this case, notice the thousandths place is 8, so we go 0.79. Okay. Now, let's talk about using this. Let's say I've got this triangle here. Maybe this is a ramp, and I want to find B to C. I'm looking to figure out this measure. We're going to round it to the nearest hundredth. So I want you to think about what parts of the triangle do you have, what parts do you want, and then what ratio is going to compare those two things. So here's my angle. First thing I do, find your hypotenuse. Across from here is the hypotenuse. Then I look at this angle, because that's the one we're going to work with, and I cover it up. And this is the side I see, so I know this is my opposite side, my opposite leg, which makes this, by default, the adjacent leg. Now I say, what do I have? What number do I have? And I have the opposite leg. So I'm going to write, I have the opposite leg. I want BC, so I want the adjacent leg. And what ratio do I need then? If you think, so, ka, toa, well, what compares opposite and adjacent legs? I'm going to need to use my tangent ratio. So the relationship I'm going to set up to find B to C is I'm going to say I'm going to take the tangent of 15 degrees, and that's going to be equal to the numerical ratio. It's going to be equal to this opposite leg, 10.2, over the adjacent leg, BC, which is what I want to find. Okay? So I've got a relationship. Remember, this is just a number, and I'm going to do a little algebra now. So this is in the denominator, so I'm going to multiply both sides by BC, and that'll cancel out. So now I have BC, the length I want, times the tangent of 15, which is a number, equal to 10.2. Well, the opposite of multiply is divide, so I'll divide by tangent of 15. And that's going to give me BC. And this is where we round. So now we put this into our calculator in degree mode, and we say, okay, calculator, I need 10.2 divided by the tangent of 15 degrees, and I can see it's 38 and we're rounding to the nearest hundred. So I look at this, and this is a 6, so it's 5 or better, so I make this a 7. So I'm going to have 38.07. I've got feet up here, so 38.07 feet. So think, have, want, need. Okay? Let's look at one more example. And big caution, don't round to that final step, because that's going to give you a more exact answer. Okay, let's look at this one. We're going to find Q to R, and we want to round to the nearest hundredth. So come over here first. We want to find this value. Let's label them all on the triangle. Across from the right angle is our hypotenuse. This is the angle we know. Cover it up. This must be the opposite leg, which makes this the adjacent leg. And we think our trig ratios are so, ka, toa. Sine is opposite leg over hypotenuse, cosine adjacent leg over hypotenuse, tangent opposite leg over adjacent leg. And I have, numerically, the hypotenuse. I want Q to R, so I want the opposite leg. I look, what compares opposite to hypotenuse? And the sine is the big winner on this one. So I need the sine ratio. Now I'm going to set up my relationship. The sine of this angle, 63 degrees, equals the opposite leg, QR, over the hypotenuse, 12.9. This one's even easier to solve because I just need QR alone. It's being divided by 12.9, so I'm going to multiply both sides by 12.9. That will cancel out. QR equals, approximately. Now I'm going to come right back to my calculator. And I'm just going to type in 12.9 times the sine of 63 degrees. And I see my answer to the nearest hundredth. This is a 3, so it doesn't, we're going to drop it. So 11.49. And 11.49, I look around for units, I see centimeters, and there's my answer. So, finally, we're not, summary. When you're doing your trig ratios, think SOHCAHTOA. Ratios are numbers. We start by writing them as fractions. Opposite leg length over the hypotenuse. Adjacent leg length over the hypotenuse. Opposite leg length over the adjacent leg length. We can set up proportions using these ratios to find missing lengths in any triangular situation. Think, what do you have? What do you want? What do you need? And the parts of a triangle in relationship to a given angle, a hypotenuse is always across from the right angle. And then to find the opposite leg, just the leg opposite an angle, cover up the angle. The leg you still see is the opposite leg. The side leg you covered up is the adjacent leg. Label those things before you start, and you will have a happy time with trigonometry. See you in class.